Hello, and welcome to the UFS webinar. This webinar is hosted by the National Weather Service Office of Science and Technology Integration. The goal of this webinar series is to enhance communication and share advancements in all aspects of the UFS in both research and operational settings. I am Stacy McKellen. I'm here to help coordinate and deliver the webinar. Feel free to contact us at OSTI if you have any comments or suggestions. If you have any recommendations for speakers that you would like to present at this webinar, you can email your recommendations to ufs.modeling@noaa.gov, and we'll take your suggestions into consideration. Okay. Today's webinar is the NOAA Precipitation Prediction Grand Challenge and Historic R2O Opportunity. Today's presenter is David Novak, Director of NOAA NWS Weather Prediction Center. Okay. Due to the high number of attendees, you will be in listen-only mode during the event, and you will not be able to unmute. If you have any questions or suggestions now or during the event, please submit them via the Google document provided in the chat. The presentation should last about 45 minutes, followed by questions and answers for about 15 minutes. Okay. Today's presentation given by Dave, Brian Gross will be introducing. Brian?
Thank you very much. Dave, I see you're on camera. So I have, it's been a real privilege working with Dave over the last 2 years as one of his fellow center directors. I wanted to note that as the director of the Weather Prediction Center, he and his center is responsible for the national forecasts of heavy rainfall, snowfall, hazardous weather. Dave and his team keep us safe. And for that, I will thank him both as a citizen and as a colleague. So Dave comes to us very highly credentialed. He has a BS in meteorology and an international relations minor from St. Cloud State University. And he received his master's in atmospheric science from SUNY Albany and a PhD in atmospheric science from SUNY Stony Brook. Now, Dave's had a very active meteorological career. He has worked as a fire weather technician in Fairbanks, Alaska. He was a meteorological intern in Duluth, Minnesota. I'm going to say he likes cold places. That's what I'm gathering. So, and he stayed, I'll say, in the northern half of the country. He joined the Scientific Services Division of Eastern Region Headquarters in Bohemia, New York in 2002. And there he was responsible for integrating new science and technology into forecast operations and facilitating training for the meteorologists in the Eastern region. So you're seeing early on Dave's focus on R2O, transition of research into operations. And in 2009, Dave became the Science and Operations Officer for the Hydrometeorological Prediction Center, the precursor of the Weather Prediction Center, which he now directs. And throughout Dave's academic and professional career, David has been involved with collaborative research and bringing operational needs to the attention of the research community, which we label O to R, and integrating promising research into operations. So Dave's been involved in the entire R to O to R chain. Dave's also had leadership positions in the Combined Federal Campaign and in the American Meteorological Society, where he was on the board for operational government meteorologist, and he was an award-winning editor. So, personally, I know Dave as a leader and a source of incredible energy in accomplishing the mission of the National Weather Service and NOAA, and I am thrilled that he's here to talk to us today. So thank you. Thanks, Dave.
Terrific introduction, Brian, and just a steadfast colleague. In fact, Brian is a co-author on this paper here. I wanted to highlight that it's really a team of folks here putting this together, and it's really been, again, across line offices here. So this is not just Weather Service, it's not just OAR. but many others as well. So there is a national imperative to improve precipitation forecasts. We've seen this damaging threat from too much or too little water, and certainly exacerbated by climate change. So even just today, I know there were some flash flood warnings for the Birmingham, Alabama area and Raleigh, North Carolina area. And I think a critical function here, a critical aspect of this is, progress in terms of our flood and drought forecasting, which we know are impacts associated with climate change. Progress in flood and drought forecasting is largely dependent on improved precipitation forecast. So this it's critical if we're going to, improve drought forecast as well as flood forecast, so it's an important aspect. Like this figure from Hunick et al. 2016, and we'll have to just kind of ignore this. I think Imprex was the name of the experiment that they were doing, but I think if you look beyond that, just kind of what the figure's showing here. So we have time scale from minute to 100 years across the x-axis here, and then along the y-axis we're looking at the scale. So, you can imagine a single reservoir or city all the way up to beyond a state to maybe a region of the country. So out on the far right side here, we have climate projections. So beyond 10 years, that's not really where we're looking in terms of the Precipitation Prediction Grand Challenge. You also have this gray area where it says it's unpredictable. And indeed, I think that is our experience, right? In terms of trying to get the rainfall forecast for a single reservoir a week in advance is beyond the science. But then let's talk about the positives here. So in the green is our current scale. And indeed, having, say, an accurate forecast for a single reservoir city, we're pretty good on the order of minutes to a few days. And indeed, can even see things such as an atmospheric river coming to the state of California, say, a week in advance. But perhaps most important on this graph is this kind of orange area here, highlighting schematically these user needs. And you can see maybe just a small portion of the user needs are covered in our current scale. And so one could imagine this green area moving further out to the right, thinking about giving accurate precipitation forecast on the scale of a river, basin, or state, all the way out from a week to a season. And so the main point here is we have a great opportunity, and again, a national imperative to aid decisions from days to seasons. And indeed, this is the focus of the Precipitation Prediction Grand Challenge. We're largely focused on global models in this, improving the forecast here in this days to season aspect to serve the critical needs of the nation. Now, we are certainly motivated by perhaps some painful statistics here. We've had painfully slow improvement of precipitation forecast in the past. So the figure you're seeing here in the upper left here is the deterministic global forecast system, the day 1, day 2, and day 3 forecast. It's the annual equitable threat score for the 1 inch per day threshold. So it turns out this is actually a score that we report to Congress as part of the government's Performance Act, and represents generally a heavy rainfall. This graph is shown over the past roughly 2 decades, and unfortunately, it's a pretty flat line. It's on the order of about 15% improvement per decade, which was about where the hurricane intensity problem was previous to HFIP. So you think about that vexing problem, I would argue our precipitation improvement is along those same lines. It is a vexing problem and a grand challenge. Shown here on the bottom is thinking probabilistically here. So the top is deterministically. Let's think probabilistically in terms of the GEF's prior skill score, say for about a ½ inch per day rainfall total here. With prior skill score, you want to be high, you want to be positive here. You can see day 5, we have some skill. Unfortunately, day 10, or the last 5 to 10 years, pretty much no skill. If you're looking at a particular 24-hour period, trying to get the rainfall in that particular time frame. And Others have noticed. Many of you are aware of the priorities for weather research report recently provided to Congress and requested by Congress through the NOAA Science Advisory Board. This is a quote. So, unfortunately, precipitation forecast skill has not improved substantially over decades and remains one of the major technical challenges in atmospheric sciences. Poor prediction skill for flood and drought has an inordinate impact on disadvantaged communities. So again, I would argue that this absolutely is a national imperative to improve our precipitation forecast. And that takes us to the Precipitation Prediction Grand Challenge. So this is a NOAA effort with the goal to provide more accurate, reliable, and timely precipitation forecast across timescales, all the way from the mesoscale weather to seasons, through the development and application of a seamless, fully coupled Earth system prediction model. So if you're in the UFS community, your ears are probably piping up here in terms of, well, I think the UFS is a seamless, fully coupled Earth system prediction model, or aspires to that. And indeed, I think that is the motive here. How do we improve many of these UFS aspects to make the forecast better, and as we'll talk about, to actually help communities in their critical decisions? So imagine what could be. So if we take that time frame out to say 2030, and we've got this dashed line here, this represents a doubling of the historical rate of improvement, roughly adding about 2 days of lead time by 2030. In terms of GEF's prior skill score, perhaps going from no skill to some skill at the day 10 timeframe. This is not easy. We've spent 2 decades getting to the point we're at, about a 15% improvement. But the idea is, with some focused investment through the PPGC, we could double this historic rate and provide communities with even greater lead time, accuracy, and specificity for their critical decisions. So the Precipitation Prediction Grand Challenge has basically a fundamental tenet that we are going to think end to end, that there's a number of different interconnected objectives, and it's not one thing, it's all of these things. So we need to enhance and sustain user engagement. We need to understand what critical decisions and thresholds our users have. There are many things about precipitation we just don't know, and so we need to advance our understanding of precipitation predictability and improve our process level understanding and modeling. We need to sustain, enhance, and exploit observations. I mean, observations are a critical aspect to the precipitation prediction problem. And really importantly here for the UFS community is this bullet on improving prediction systems for precipitation. So we'll be focusing mostly on this aspect. And then also, and fundamentally, the end of the value chain here is improving prediction products and applications for better user decisions. So I just want to emphasize, it's not one thing, it's all of these things. And we'll talk about how, it can be difficult. We want to maybe focus or have focused investment in one of these areas, but then you just run into a bottleneck in another aspect and aren't actually getting the decision makers the information they need. So you need all of these interconnected objectives. With that said, UFS community, UFS seminar, I wanted to focus here on improving prediction systems for precipitation. And if you dive into the NOAA strategy here, what it actually says here is a goal here to improve the unified forecast system precipitation forecast by addressing errors from initialization. So thinking about initial conditions in the UFS. The middle bullet here of improving precipitation forecast by addressing errors in model biases. We know we have many biases in our models, and we'll talk a little bit about some ideas of how to improve that, particularly through perhaps improved physics. And then the last bullet here, a focus on coupling. We know it's an Earth system, and so there are other components beyond the atmosphere that are important to prediction. And so that is the fundamental strategy here, getting at the model initialization, the model biases, and approaching this through a coupled modeling approach here, which again, not by surprise, aligns very well with the UFS efforts. Also, I wanted to highlight this kind of intersection between the Precipitation Prediction Grand Challenge and the UFS applications. This is the so-called rainbow chart, and just focusing on the far right here, just highlighted in arrows, all these different UFS applications that would be improved through investment in the Precipitation Prediction Grand Challenge. And you see it's almost all of the various UFS applications. So I think there really is quite a nexus between what we call PPGC and the UFS applications. So I wanted to highlight some of the gaps and challenges that we've documented and observed, and I'm sure many of you will resonate with many of these. And let's first just focus on the short to extended range time period, kind of in that first few days to about a week. We had various working groups set out across NOAA, and one of these working groups was on model systematic errors, and they came up with basically a listing of various aspects, including the underestimation of heavy rain and overestimation of light rain, the diurnal cycle of precipitation with maxima too early in the day frequently, the initiation of convective precipitation. You'll see convection being a common theme here, a slow or non-physical propagation of convection, the phase speed of mid-latitude troughs. For example, we know the GFS system generally has a fast bias with upper level troughs, and actually the European system generally has a slow bias with mid-latitude troughs. As we get to longer time frames here, the subseasonal tropical variability represented by the MJO and how we represent that, and then the vexing double ITCZ challenge that, of course, we see even in our subseasonal models and extending certainly into our climate models. And the critical aspect is these kind of model errors lead to ensemble under dispersion. In other words, we're too confident in the wrong solution. And that's a bad place to be, right? Think about if you're providing decision support or communicating with a mayor of a city, and you're using the best of the science, you're using ensembles, you're doing everything they taught you to do with probabilistic information, but it turns out those probabilities aren't quite calibrated or correct. So these systematic errors can have a real issue, and we need to address them. So in thinking about this, I mean, your mind might go to a variety of different aspects. And I guess I want to make the point that, again, there's no silver bullet here. So it isn't just a matter of, say, model resolution or using different ensemble designs or even data assimilation. And I make this point through this paper, Yusuf and Knopfmeyer, 2019. So they were using state of the science here, 36-member, 3-kilometer ensemble with rapid radar data assimilation. And they ran this system on 5 flash flood cases. So on the far right here, just showing in each of these 5 cases, on the left here is the forecast, and on the right is the observed. And you can look, there is correspondence. I mean, at a general level, there is a prediction of these. But if you're looking at a particular county, so for example, this is Houston, and in this case, it looked like it was going to be about a county or two to the east in terms of the heaviest rainfall. Again, these are very short range, 0 to 6 hour forecasts. And in fact, it was Houston that was in the bullseye here with a devastating flash flood. And so if you quantify this on the left in terms of the fractional skill score of 2-inch-an-hour rainfall rates, again, very high level, hard to nail down a 2-inch-an-hour rainfall rate. But indeed, and it depends on how you smooth. I mean, if you smooth it, you get higher fractional skill score. But the bottom line is you only have some skill for these really high impact, heavy rainfall features out to about 3 hours with our most sophisticated state-of-the-art ensemble systems. So that's a challenge. That's a gap. We know model microphysics certainly matters. So this is a figure from Clark et al. 2012, looking at composite frequencies of the forecast location of precipitation features versus the observed features in the shading. So what you want to see here is actually what the Thompson scheme provided in this case, where your observed precipitation max is at this dot, and or your forecast is at that dot, and the observed frequencies should really cluster and be high around that dot. I mean, in an ideal sense, it would collapse to the dot, right? But you look at the variety here of the Morrison. There's a location displacement here, and the WSM there's some magnitude differences. And I know we have, this was almost 10 years ago. I know we have other schemes now, and it'd be interesting to do this study. The point here is that there is a wide variety in precipitation skill just based on the microphysics that are used in the prediction model. And then we know convective parameterization certainly matters. So this is a figure by Piersante of 2021, looking at a Rober diagram of skill here on the left. You don't need to know all those details. The main point is these clusters that we see here in the red, for example, are all the Kane-Fritsch members, the Grell-Freitas and the Tiki. You can see how clustered they are. And so this is, again, a performance diagram for precipitation over the CONUS using 19 ensemble members of varied convective parameterizations, microphysics, and PBL schemes. And it collapsed basically onto the various convective parameterizations. So clear clustering around the CP schemes. So that's not what you want in a ensemble with various convective parameterizations, microphysics, and PBL schemes, right? But you'd want some even spread, if you will. So again, convective parameterization certainly matters. And just auguring in a bit on this challenge. Many of you who may have gray hair like me might remember the Gridscale Feedback issues of the 2000s, and perhaps before that, grid point storms. And we really kind of thought we had this solved to some degree, certainly in global operation modeling systems. I know there was some incredible work and some good implementations around 2010, 2011. I think that helped us out in the GFS. However, as we move into the FV3 world and have to kind of think about convection allowing and tuning of the system, we're starting to see the issue again. So this was from 2020, but we had similar results from the 2021 experiment. And I know we're slowly getting at what may be causing this, but we know that the current generation of parameterizations of deep convection are local. So convection is treated independent from one grid column to the next. It doesn't necessarily communicate as much across grid points. And then it's also not scale aware. Statistics not consistent when applied from finely resolved to coarsely resolved scales. And I do know there's various ideas of, do you need a light convective parameterization even at 3 kilometers to kind of help this issue. But I guess the point is, convective parameterizations, it's a hard challenge. And then you might say, hey, we've solved the synoptic problem, right? We're good there, right? Well, we're getting better, but this is an updated graph of the percentage of the GEF's 5-day 500 millibar height forecast that verified outside the expected envelope of a 30-member ensemble. So it actually already accounts for the fact that you should, with just 30 members, you probably have about 6% of the time that you miss on the edges. This is the percentage above that threshold. And you can see this, I guess, was over the past couple of months in this cool season. And you can see, I mean, there are areas in the Pacific here where you're over 10% of the time where the GEF's 5-day height forecast verifies outside the expected envelope. So, the synoptics are still an issue. And this, again, gets to the point of the under dispersion that we see. We know these ensemble systems are often run at a coarser resolution than high impact features of interest. I know we're working on that, and that contributes to some of this under dispersion, but still a existing gap. And this was a nice example of even just small problems in the synoptics can result in a big problem in precipitation. So on the left here, this is a day 3 forecast valid about a year ago in the Colorado area here. This is on the order of 7 inches of precipitation in the foothills of the Rockies here. Now, a historic snowstorm occurred, okay? but it was about half the amount here. And so if you look on the right, this is a sounding focused in. The forecast was much warmer, and actually look at the screaming easterly upslope flow in the forecast. And what was actually observed was a little bit of cold air damming, light northerly winds with the screaming easterlies and upslope flow above it. But this was due to just a small error in the synoptic flow, resulting in too deep and strong upslope flow in the model forecast. So again, these synoptic differences really make a difference in terms of the eventual precipitation forecast. So it's a challenging problem. So so that was on the short range, right? So we'll just hit you with some more bad news, and then get you with some good news here. But here's some more bad news on the seasonal to subseasonal timescales. So this is an example where we're looking at regime transition and the failure to predict the end of the drought in California in 2017. So looking at the California percent area in the U.S. drought monitor, and you can see you've been transitioning from a multi-year severe drought to near normal conditions with record flooding in the span of about 60 days. And all models failed to predict this transition of the large-scale atmospheric state, and really just did not have a sense that heavy rains were going to occur beyond about 2 weeks. So there's some various, science questions here. What caused the breakdown of the ridge? I guess this was in a La Nina state, so not what you would expect, and perhaps there were other tropically forced teleconnections. But we certainly see these kind of issues in the subseasonal time frame. And we also see, for example, SST issues in the equatorial Pacific. So this is a graph of this CFS version 2 forecast of the SST for the Nino 3.4 region at both 3-month lead time, that's in the blue, and 6-month lead time in the red. And you can see in these circles, these lines certainly do not match the black, which is the observed SSTs. And in fact, getting above 1 degree here, you're getting into prediction of El Nino that did not occur a couple of these times here. So we have more work to do here in this subseasonal time frame, getting the SSTs correct, for example. And then many of you are aware of this in terms of the systematic precipitation errors. This was a paper by Flato et al. 2013 looking at some of the CMIP5 models. And here was the multi-model mean precipitation, and then here was the bias. And these are large biases, almost a doubling of what occurred with some of these biases here, particularly in the tropics. And you can also see some dry areas as well. So major errors in the distribution of the mean precipitation, including the development of the erroneous double ITCZ back here in the Pacific. And then, these were climate models, but certainly our coupled models used for S2S prediction have very similar errors. And one of the points I know Dr. DeWitt from CPC has been highlighting is these errors show up pretty quickly in the forecast run, and they develop pretty rapidly on the order of 1 to 2 months. So you might say, well, yeah, of course, those climate models and maybe S2S models, what we really need to do, and I'll admit this is where my head was at, what we really need to do is just, why can't you run a global 3-kilometer convection allowing model, right? Isn't that just the answer to everything here? And turns out we're getting to the point to actually test that hypothesis. So this was a recent paper by Caldwell et al. 2021. It was a 40-day convection permitting global run. I mean, it just boggles your mind. This is exascale computing using an exascalar system model. I'm focused here on one of the figures they had, and it's a huge computational expense. But so in exchange for this huge computational expense of doing a 40-day convection permitting run, that you can resolve deep convection in all parts of the globe, it does improve many but not all of the long-standing climate model biases. Particularly, you still have many of these biases that are common in the tropics, including tropical precipitation biases, and again, quite large. So all of this to say, once again, so even running a global convection permitting, a system with, fancy state-of-the-art, aspects isn't going to solve all our problems. And I think part of the point here is there's no silver bullet. It is an integrated system. You need improvements in data assimilation. And in fact, this was cited 241 times in the recent Priorities for Weather Research report. Coupling, we know, again, it's an Earth system. And so we need to take all parts of the, the atmosphere, the hydrosphere, the cryosphere, all ocean aspects into account. We know all these various simplifications we have in modeling with PBL and convective parametrizations, microphysics. Resolution is important. I mean, it helps, it doesn't hurt, but it's not the single answer, for example. And we know that ensemble configurations are important, but if you have some basic biases, whether you have 10 members or 30 members, it's not necessarily going to solve that issue. And I think this is one of the challenges, right? I mean, in the Priorities for Weather Research report, I think, and often, in thinking about investment, we try to prioritize. Well, I know you said all that, but really, what is the one thing that you can do that we invest in that will make it better? And we've been, as part of this NOAA Precipitation Prediction Grand Challenge, I think we've been trying to hold true to the tenet that it's all of these, and you actually need investment in all these areas, because otherwise you're going to have an Achilles heel and have a bottleneck somewhere in the process. Okay, I didn't mention operational computing. Now I am. So another aspect here, of course, of this grand challenge is our operational computing gaps. So the good news, of course, is that we are currently going through the process in 22 here of getting a 12 petaflop operational system and WCOS here, which is critical. You see all the statistics below here. This is important for GEFS version 13, GFS version 17, the rapid refresh forecast system and HAFS. Except when we're done with all that, we will have filled that supercomputer. And you might argue that UFS requirements are perhaps even a little beyond where we are, operationally. Now, remember, our goal with Precipitation Prediction Grand Challenge in a modeling context is to double the historical rate of improvement that we've been seeing. So we need to do better than that. And I have really more compute than UFS is requiring. So you might imagine, something like this slope through time. And then you get the Priorities for Weather Research report that, cites that really to stay on the cutting edge, of all these different aspects of precip, Earth system prediction model, kind of getting towards that global convection permitting type of system, 1,000 petaflop mean. So what the axis here is 25 petaflops. I imagine that's up towards the roof here in terms of this linear graph. So the point is, this takes HPC, and that's part of that end-to-end need. You need the improved modeling, and you need the improved, access to HPC here as well. Okay, so that was all the downer stuff. Now some good stuff. I mean, that's all part of the challenge, but gosh, we have some of the best scientists and practitioners in the world working on these things, and we have seen some recent progress in improving prediction skill. So for example, we've seen some progress in the Shortrange QPF. This is a figure from the HER equitable threat score of the 1 inch per day threshold. Again, that's kind of a common threshold for heavy rainfall, reported as the official Weather Service GIPR Performance Act score. But in any respect, you see, again, there's kind of this positive trend with both the HER and the RAP through time. And in fact, you do see the impact of resolution here, for example, comparing the 13-kilometer RAP in blue and the 3-kilometer HER in red. And in general, the 3-kilometer HER is a little bit better. And so, we have seen long-term improvement for the short-range, rapidly updating model. attributed perhaps to data assimilation. We know the HER uses improved use of radar, surface, and cloud observations, for example. And the model has better physical parameterizations, and we've gotten improved representation of the diurnal cycle. So, you know, there's a positive story there. And a big kudos to EMC and the modeling community here. The GEFS version 11 and previous versions were really, really under dispersive. And in fact, you can see this with the reliability diagram here. So the previous system was in black. The GEFS version 12, that's now operational, in red. You want to be close to this blue line. You can see the red is a lot closer than the black line to this ideal blue line. And in terms of Breyer's skill score, huge improvements here. If you look at the previous system in the black versus the GEFS version 12, you see huge jump up in skill. And just, you know, just to show one case, pretty typical here. You know, previous versions of the GEFS, you'd have these very black and white kind of yes, no kind of solutions. And you're seeing a more realistic kind of probability now with GEFS version 12. So terrific. And if we look to the S2S range, these are pretty fresh results of the UFS coupled model improvements in the MJO skill. So in the blue turquoise line here is the CFS version 2, looking at the various parts of the MJO. And this is anomaly correlation and then by day, so going from 0 days out to about 33 days of prediction. And you can see, and these are all various experiments in the other colors here. You see just almost a paradigm shift here to the right, which is improved prediction, a greater lead time here in the prediction of the MJO. So a dramatically increased skill of MJO from improved UFS physics and coupling, which is a good news story for sure. And then I want to highlight the NOAA Testbeds, and particularly here the hydrometeorological testbed. This is focused on improving precipitation and serves as a forum to bring our communities together in terms of meteorologists, hydrologists, modelers, forecasters, academics. Bring these different experts together, these different perspectives, and really focus on the improvement of precipitation. And we've been testing new forecasting and verification techniques, evaluating the UFS applications, and providing that back to EMC and OAR, and kind of through this iterative process, making some of these innovations. So again, a good news story here in terms of the progress that we've seen in our NOAA testbeds. So so that was all under the hood, under improved prediction systems for precipitation. But that's not enough. That's not enough. I want to get to this last bullet here of improving precipitation prediction products and applications. So some of you have probably heard or seen this quote, and maybe a bit too frequently, but I think it's because it's so true. This is from Alan Murphy, 1993 weather and forecasting paper, that weather forecasts possess no intrinsic value. They only acquire value through their ability to influence the decisions made by users of the forecast. So perhaps Dr. Alan Murphy was ahead of his time as we think the Weather Service moving into an IDSS framework here. But this point is, you could have the very best model forecast, but is that going to influence a community leader's decision? And so we have to kind of connect the dots here. And some of the aspects of the Precipitation Prediction Grand Challenge here are connecting those dots, of translating the model forecast into actionable information for critical decisions. These are various tools that are either in experimental or developmental stage. So for example, you can mine the href system for the probability and track of extreme rainfall systems, that's shown here in the upper right. Helps a forecaster quickly interpret that, for example, there is a favored corridor here of an MCS across northern Wisconsin, coming up. Many of you have seen the extracting weather scenarios of the probabilistic snow forecast. We're also doing this for precipitation at a few locations, and you can have, for example, a low end amount, a most likely amount, and a high end amount. that provides a very simplistic view at scenarios. We're trying to do more complex mining of ensembles through formal cluster analysis to derive scenarios. But that's an example of the kind of tools that we could support through the PPGC. And then one of the things we're really excited about through the disaster supplemental coming up here is an urban rain rate dashboard. Look at the probability of hourly rainfall rates exceeding stormwater design criteria for major cities, and highlight when in the predictions, say in the next 24 to 36 hours, those thresholds are above a certain probabilistic threshold. So these are the kind of ways to use the improved numeric weather prediction to actually influence community decisions. And then, of course, you could have more static products translating, these forecasts into actionable information. Something I'm very passionate about is the connection between the weather and subseasonal time frame. And I think we can do this through establishment of day 8, day 9, and day 10 probabilistic daily precipitation forecast. In essence, extending your day 7 forecast out to day 10, your daily day 7 forecast out to day 10. And we have some prototypes, but looking at the PPGC to actually get that across the finish line here. Improving week 3 and 4 forecast, we know that's that area where there are numerous stakeholder decisions that can be improved. Flash drought services are another key area. And then, as we were highlighting, there are various tools such as the Extreme Forecast Index and other AI-powered applications that would be useful to decision makers. And yet, that's still not the end of the line. There is a human aspect here to decisions. And, in the Weather Service, we call this impact-based decision support, where you're on the front lines with the decision maker, helping to translate that model information, those tools, those products, into helping the decision maker make the best weather-sensitive decision they can make. And so, so I think you see this whole value chain. I didn't start at observations or base level understanding, but that is important too. But you certainly see how the model to the products to the IDSS is so critical, and how we're going to really address this grand challenge. So again, these objectives accomplished by co-developing, partnering with our end users, partnering with initiatives such as UFS, also the S2S subseasonal to seasonal initiatives, and EPIC. I think there are opportunities for greater collaboration there. One of the things we've been trying to get is investing in reanalyses and reforecast. We think for precipitation, reanalysis and reforecast are a critical foundational infrastructure that will help improve precipitation forecast. We know machine learning and other artificial intelligence tools can also help. And then I'm a strong believer in test beds. I think they're, bringing the communities together, sharing the different perspectives, have an iterating process are really critical to transitioning new precipitation capabilities. So there is some good news. We do have some ongoing PPGC efforts. In the FY22 budget, we're still sorting some things out here, but even amongst the programs of EPIC and S2S and USWRP, precipitation is in there, and we want to continue to support that. In the 22 Infrastructure Act, there is a focus on modernizing precipitation frequency, thinking this will be the Atlas 14 data set and probable maximum precipitation studies. So looking forward to that to help put precipitation in context. And then the disaster supplemental, we have investment across the lines here from social science, kind of the user engagement aspect, process studies, satellite data infusion, model development, and product and tool developments. And so we're trying to be true to our word that this is an end-to-end problem, and we need to work it through all these different components. And we're excited soon to get the go-ahead to actually get going on the 22 disaster supplemental improvements. So I hope you have a better sense for what the Precipitation Prediction Grand Challenge is. And I really view it as a historic R2O opportunity to improve precipitation prediction skill. In fact, I would say it's once in a many decade opportunity here. And we need to. You saw those model skills. You see what happens every day in the news with these water extremes. We need to do better, and this is a strategy to help get us there. So I think right a bit on time. And with that, I'll turn it over back to the facilitator. Take some questions.
Thank you so much, Dave. That was a lot of information and it was very interesting. So we do have a bunch of questions, and if you are able to click on the chat and click on the Google document, you'll see the questions, read them, and you'll be able to answer them.
Yeah, let me see. I'm going to stop showing my screen here.
Okay, yes.
Okay. Yes, I can. Did you want me to read them off, or?
Yes, please.
Yeah. So, so from Warren Blair. Hi, Warren. Great to see you virtually. How much further ahead might we be if A, the hyperspectral environmental sounder was included on the GOES 17 satellite series as originally planned, and B, a full 40 VAR was used in initializing the GFS? Yeah, you know, these are certainly critical aspects. We know the vertical profile of the atmosphere is important for prediction. And we also know that, you know, data assimilation is a critical component. You know, I don't think we can say exact, unless you're doing specific OSSEs and, you know, comparison studies and such, you know, it's hard to, I mean, that's how you'd quantify that difference. But I think the point is, yes, it would be good. This is the whole point, is these things such as, you know, vertical profile of the atmosphere, how we take observations and improve data assimilation are right in the wheelhouse of what we need to do to improve forecast scale, including precipitation scale. So hopefully that answered the question. From Matt Rosenkrantz, there could be some paradigm changes, changing advances. For example, AI, machine learning can make the models much more efficient. Cloud can get us access toward that 1,000 petaflop line. We run global models 4 times a day. Do we really need to? What is our ability to redo the entire way we do things? Yes. Yeah, I mean, I think the world is changing, right? And we have these great opportunities with machine learning and AI and you know, potential for, you know, exascale compute. We also have, of course, our mission requirements. And so there's always been this balance of how do you, you know, use and leverage the latest technology while not breaking something that's already working, right, in some respects. So yeah, I mean, I share an aspirational view. I think, you know, part of the Precipitation Prediction Grand Challenge effort here is to highlight we have a problem in precipitation prediction. We have a need. I mean, we see communities getting flooded. We see communities suffering through drought. And we have an opportunity here to invest in some of these new technologies to make precip better. So I think we're trying to organize NOAA and rally around that challenge and consider some of these things such as, you know, AI aspects and, you know, how we might conserve and best use our available compute. Dave Helms, hi Dave, good to see you. What is being done to observe and predict flash drought? Oh, flash agriculture and flash drought. Admittedly, that's probably outside of my expertise here. I know my colleague, Dr. DeWitt, from CPC and many others, of course, would have information here. But I do know that is one of the things in the Precip Prediction Grand Challenge that we're highlighting as a service for users. We know, you know, I think a few years ago there was a devastating flash drought in the Corn Belt, and really raised interest in this challenge. So, and just in general, a flash drought is a drought that develops extremely quickly, say on the order of 2 to 3 weeks. And you might imagine you get some sort of blocking pattern or some sort of subseasonal pattern that is just persistent. So yeah, I mean, I think that is within scope of the Precip Prediction Grand Challenge. From Michael, how are you reaching out to the non-NOAA community to get help? I am a machine learner that wants to help. Wonderful, wonderful. Yeah, I think we've started. Well, first we wanted to get our act together a little bit in NOAA to ensure that the line offices are aligned with our various goals. And I think now is the time to start reaching out. We have had some engagements at AMS, and I think through various requests for proposals that may be coming, we'll see. Depending on budget and programs, that might be a way. But I think it's through starting to get the word out and pound the pavement a little bit, just like this seminar. Yeah, if you wanted to drop me an email or such, that'd be great. Yeah. I don't want to raise expectations too high for RFPs, but that is one of the traditional manners in which NOAA is able to fund, for example, academic partners. So, yeah. Let's see here. Those were great questions. I'm not seeing more.
Yeah, it looks like that's it. Someone's still responding to the question that you just answered.
Yeah. And I do want to highlight a lot of credit to, on the title slide there, a whole variety of individuals behind the NOAA Precipitation Prediction Grand Challenge, bringing it to this point. And I think, main point is we do have a problem. We're working on it, but it is going to take kind of an end-to-end, almost a decadal approach to this problem.
Okay. Yeah, it looks like nobody else has any other questions. And again, I want to thank you so much. This was so informative. My colleague and I were just chatting about it, saying that this is a lot of stuff that we do in our line office. So, it's very informative for us, very informational. I appreciate that.
Absolutely. Well, I appreciate everyone's time and attention. And again, on behalf of the PPGC team, we're very interested in feedback, very interested on how we can make programmatic and tactical progress on this grand challenge. Yeah.
Absolutely. Thank you so much again. And I want to also thank Brian Gross for that great introduction. Brian, if you're still on, thank you so much. We really appreciate that you can join us.
Oh, I am thrilled to be able to join, and it's been, like I said, a pleasure serving with Dave and participating with him on this Precipitation Prediction Grand Challenge.
Right back at you, Brian. Yep.
Okay, well, if nobody else has any questions, I think that we can adjourn the meeting. And thanks again. This is so interesting. This webinar was recorded and it will be posted on our UFS webinar page. So be looking out for it. And it's also going to be posted on the Weather Service YouTube channel as well. Thanks again, everybody. And from now, the meeting is adjourned. Enjoy the rest of your day.